So, yes, so what is that we saw? We saw something. What is that we saw? We saw that, yeah, there exists. Yes, so this is what we saw. There exists a disjoint collection. In fact, a countable pairwise disjoint collection of sets obtained from using axiom of choice. For which countable additivity fails. For which countable additivity fails. Right. Fine. So with all these things, so well, at least can you expect at least finite additivity? Why finite additivity? At least for two sets can we expect? Well, as a corollary, there exist disjoint sets. E and F of R such that M star of E union F is strictly less than M star of E plus M star of F. Yes, so let's look at the proof. So we are going to prove this by contradiction. Suppose that for any two subsets E and F of R, M star of E union F, in fact, I need disjoint. That's very important. For any two disjoint subsets E and F of R, M star of E union and F equal to M star of E plus M star of F. So we will have to produce a contradiction. Yes, so if it is true for two sets, then what can you say further?
True for like 10 sets.
Yes, why? Because of
Mathematical induction.
exactly right. So a direct application of induction will tell you that by induction it follows that if ek k running from 1 to n is a pairwise disjoint collection Pairwise disjoint is a pairwise disjoint collection of sets. Then m star of the union k running from 1 to n ek will be summation k running from 1 to n m star of ek. Right. So this is what we have. Fine. But only thing that we know is that there exists a countable pair of disjoint collection of sets for which countable additivity fails. Right. So now we will have to show that once you have this additivity for finite number of sets, then we are going to have additivity even for countable number of sets.
Infinite.
So infinite means, yes, countably infinite, right? Exactly. So let ek k in n be any countable collection of subsets so far. Then summation 1 to n m star of ek. Yes. Well, all these are disjoint. Just now we saw. Therefore, this is same as m star of the union 1 to n ek. Fine. But this union, finite union, is contained in the larger union, that is 1 to infinity. So this is less than or equal to, by monotonicity, m star of union over k in n ek. But m star is countably subadditive. Therefore, this is less than or equal to summation over k in n m star of ek. And this is true for all n in n. This is true for all n in n. What is so? Your left hand side there is an n, and then the right hand side it is independent of n, which means that this is true for all n in n. Therefore, letting n tend to infinity, what do we get? We get m star of the union is equal to summation over k in n m star of ek. That's it. Done? Right. But this is impossible. This you cannot expect, because that's what we saw in the beginning, that there exists a countable pair of countable pairwise disjoint collection of sets for which countable additivity fails. So, which means there exists a pair.
Sir, can you explain the last argument again, please? How can we let n to be tending to infinity?
So this is true for all n, and therefore let n tend to infinity. That's what I'm doing. Is that clear? This is true for all n, and therefore I'm letting n tend to infinity. Right?
So can we do that? Like,
can we do that? That means
Can we let n be to tending to infinity?
Why not? Why not?
So like,
Your
doesn't it?
right hand side, it is independent of n. Your
Yes,
right
sir.
hand side terms, they are independent of n. And therefore, I can do that.
Okay, sir.
But sir, even if we do that, how can we ignore that possibility of less than? I mean, we have written less than equal.
Wait. So on the left hand side, you will have, in that, if you let n tend to infinity, on the left hand side, you will have 1 to infinity m star of ek. On the right hand side, you will have summation over k running from 1 to infinity m star of ek. In between, you have m star of the union. That's exactly what I've written.
Okay, sir. Okay.
So thus, there exists a pair E and F of subsets of R and F, which are subsets of R, such that E intersection with F is empty, but M star of E union F is strictly less than M star of E plus M star of F. That's it. Fine. So we wanted something which is additive on disjoint sets, because that's one of the properties of the length that we have been seeing. So at least we wanted this additivity. So once you know it for finite sets, then we know. Just now we saw how to extend it for countably infinite. So natural one is how to get this one, so-called countable additivity, or at least finite additivity, right? So what is clear from the discussions that we had, or what has been happening, it tells us that it doesn't happen for all subsets of R. That's what it says. So M star, it is defined for all subsets of R. So which means that if your M star is on all subsets of R, you get subsets for which this additivity fails. So are there a class of subsets for which this additivity actually holds? Yes. So in order to find that class, so here is so we'll see, look at a new. Let me begin with a definition. Motivated from what we actually wanted, we are defining this. A set E subset of R is said to be Lebesgue measurable if for any A subset of R, M star of A is equal to M star of A intersection with E plus M star of A intersection with E complement. So now we shall denote by script M the collection of all Lebesgue measurable subsets of R. Right. Yeah, so here are some simple observations. Right. So first one is that, well, is this collection non-empty? Scriptium. Can you give me one set which belongs to the scriptum? Just give me one set which belongs to this scriptium.
R itself.
Ah, exactly. R and then even the empty set both belong to scriptium. Yeah, this you can easily notice. Why? Well, why does R belong to scriptium?
So the complement of R is phi, and A intersection with phi is phi, and we know the measure of Lebesgue outer measure of empty set is 0. So
Yes.
and
So
similarly, we can do
if
for
you choose R, then its complement is empty, and therefore A intersection with the empty set is empty. And therefore M star of an empty set is empty. But A intersection with R is A itself. And therefore it's nothing but saying that M star of A is equal to M star of A. And therefore same argument holds even for empty. Right. Second thing, if you notice the definition, it is symmetric in E and E complement. And therefore E belongs to EM implies E complement also belongs to M. Right? Because from the definition, it is a direct consequence of the definition. Third one, if E belongs to M, sorry, if E belongs to R, E subset of R. If E subset of R and M star of E is 0, then what can you say about this E?
Is countable.
Can you repeat? E is? Can you repeat? E is?
Countable.
Yesterday we saw, right, that the Cantor set has got Lebesgue outer measure 0. But it is uncountable. There are uncountable sets which has 0 Lebesgue outer measure.
chemistry complement intersection.
E is contained in script M.
Yes. And why? Why does this E belong to script M, or the E is a Lebesgue measurable set?
For any set A intersection E is a subset of E, and
Right.
hence M star A intersection E is 0, and the other one is nothing but M star A intersection E complement. I mean, for that M star A equals to M star
You haven't finished.
I just forgot the argument.
Right. So now let me give a proof. Proof is quite easy. So let A subset of R. Now A intersection with E is contained in E. That implies M star, well, I'll simply 0 less than or equal to M star of A intersection with E. Using the monotonicity, this is less than or equal to M star of E, but M star of E is 0. And therefore, this implies that M star of A intersection E is 0. Now, on the other hand, A intersection E complement is contained in A. And therefore, this implies that M star of A intersection with E complement is less than or equal to M star of A. Right. Therefore, what we wanted is M star of A, which I can write it as M star of A intersection with E union with A intersection with E complement. Now use the subadditivity. This is less than or equal to M star of A intersection with E plus M star of A intersection with E complement. But M star of A intersection E is 0. And therefore, this is same as M star of A intersection with E complement. But A intersection with E complement, this is less than or equal to, just now we saw that this is less than or equal to M star of A. Done? So thus, M star of A is equal to M star of A intersection with E plus M star of A intersection with E complement. That is, E belongs to M. Right. So we have shown. Fine. Yes. So before we proceed, let me make a remark. So we know that M star is subadditive, and therefore M star of A. So the first two lines, these two lines, I haven't used anything about E. These two make sense for any sets. Therefore, M star of A is always less than or equal to M star of A intersection E plus M star of A intersection E complement for any A and any E. It is independent of the choice of the set. So, thus, in order to show that E belongs to M, it is enough to show that for any A subset of R. So it's enough if we can show that M star of A is bigger than or equal to M star of A intersection E plus M star of A intersection E complement. If we can show this part, then we are done. That's it. So if we can show this part, then we are done, right? And that's exactly what we are going to do. Right. So what is our aim? From now onwards, we are going to show that this M star is subadditive on finitely subadditive and countably subadditive on this class of Lebesgue measurable subsets. Right? Whenever you get a countable collection of pairwise disjoint sets or a finite collection of pairwise disjoint sets, then it is going to be additive, not just subadditive, it is going to be additive. That's the main thing. Second thing, that this M star, so this M, so when you say, see, in the case of subsets of R, whenever you choose a countable collection, it is again a subset of R, but we do not know. When you choose a countable collection and take their union, is it again a Lebesgue measurable set? So we will show that the script M is closed under finite union as well as countable union. So these are the things that we are going to see. Right. So let me begin slowly with some lemmas, easy lemmas in fact. Yeah, so let's begin with what we wanted. Direct, let E1 and E2 be disjoint subsets of R. If E1 or E2, if E1 or E2 belong to script M, then M star of the union is equal to M star of E1 plus M star of E2. Yes. So even if one of them is Lebesgue measurable, then you get this one, right? Proof. Yeah, so without loss of generality, let us assume that E1 belongs to M. So you don't have to prove it for E2. That's what I wanted to say. Assume that one of them belongs to, so I have assumed that E1. Right. Then, so we will have to, then we'll have to show that M star of E1 U2 E union E2 is equal to M star of E1 plus M star of E2, right? M star of E1 union E2. Yes, so E1 belongs to M. We are going to use this fact. So E1 union E2, it's a subset of R, and E1 is measurable, and therefore this is same as M star of E1 union E2. This is the set intersection with E1 plus M star of E1 union E2 intersection with E1 complement. Right? So we have made use of the fact that E1 is measurable. Yes. And now E1 and E2 are disjoint. And therefore, what is this one? E1 union E2 intersection with E1.
E1.
E1. The other one?
M star E2.
E2. That's it. So we are done. Right. As a corollary, let E1, E2, En be a finite collection of pairwise disjoint Lebesgue measurable subsets of R. Right. Then M star of the union is equal to 1 to n M star of EK. Yes. Yeah, the proof is easy. There is nothing very difficult. So you will have to just use induction. So I'll simply say exercise. So what you wanted is one of them. In the previous one, you want one of them to be Lebesgue measurable, and we have made use of it. So in particular, if you choose two, both of them to be, there is nothing wrong. And once you know it for two, then you know for n sets, and therefore for countable. We have seen all these we have seen. The proofs we have already seen how to move from finite to, sorry, 2 to finite, arbitrary finite, and from finite to countable. We have seen. So I'm just rewriting the whole thing, whatever we have done. Countable collection of pairwise disjoint Lebesgue measurable subsets of R. Then M star of the union will be same as summation over k in n M star of ek. That's it. So we have got this countable additivity on the collection of all Lebesgue measurable subsets. Right. So let me also add one more corollary. And this is exactly where we started with today's one. Where did we start? We started with this fact that there exists a countable pair. And as a result, we were able to produce disjoint subsets for which this is not true, that the finite additivity is not true. Right. So even if one of them is measurable, either if E or F in that case, even if one of them is measurable, you would have had M star of E union F to be M star of E plus M star of F. That if both are not measurable, only in those cases, you are going to have a strict inequality. So the corollary is that there exists subsets of R which are not Lebesgue measurable.
Sir?
Yes.
Sir, in the above corollary, how much EK we should be measurable sets?
How much means?
Means to in n equal to 2 case we have one.
Yes.
Which, yeah.
Yeah. So that is only to say that even if one of them is measurable, then you get an equality. So if all n sets are pairwise disjoint and they all are Lebesgue measurable, then you get an equality. So here you wanted all the sets to be Lebesgue measurable.
Okay, sir.
Sir,
Huh.
does the finite additivity fail for all known Lebesgue measurable sets? Like, can I have two known Lebesgue measurable sets in which finite additivity holds?
Maybe.
Okay.
We do not know.
Okay, sir.
Maybe there may be sets, but whole thing is that there are sets which are not Lebesgue measurable sets, and as a result, you may not get the finite additivity everywhere. What is assured is only on the class of Lebesgue measurable subsets.
Sir, in case of finite pairwise disjoint Lebesgue measurable subsets, can we get carried away with n-1 Lebesgue measurable sets?
Yes, exactly. You are right. You could have done even for n-1. That's right. You could have chosen n-1 sets and then one set to be non-measurable. The proof holds. Whatever we did there holds. That's right. You are right.
Okay, sir.
But only thing is that to write down what it is, we need something else there. We should know that the remaining union is also Lebesgue measurable, which we haven't shown. So that part will have to be a bit careful. So therefore I haven't used that. Yes. So before we do that, so I still have 5 minutes time. Right. So now let's proceed. Now we will have to show that this collection is closed under finite union and countable union. Right. So the collection of all Lebesgue measurable sets is closed under finite union. That is, if you have E1, E2, En belongs to M, then their union 1 to N Ei belongs to M. Proof. So as usual, so it is enough to prove it for n equal to 2. Right? I'll simply say y, and I suppose you all know the reason. The general case follows from something else. Right? Yes. So let E1, E2 belong to M. Yes. Now we'll have to show that E1 union E2 is Lebesgue measurable. Yes. So let A subset of R. Fine. So first thing, note that A intersection with E1 union E2. This is equal to A intersection with. So I'll write this union in a different fashion. E1 union with E2 intersection with E1 complement. Now use the fact that this intersection distributes over union. So this is going to be A intersection with E1 union with A intersection with E2 intersection with E1 complement. Right. Therefore, M star of A intersection with E1 union E2, which is same as M star of A intersection with E1 union with A intersection with E2 intersection with E1 complement. Right. Now this, where am I? I wanted to write something else. That's exactly what I wanted. No, I'm missing something. Yeah, these two are disjoint sets. I need one of them to be Lebesgue measurable. Only then I can be. No, not all subsets. Right. No, these two are disjoint, but I wanted something else. I wanted them to be I have taken this even part and then this part. Just give me a minute. Sorry. Fine. So I have. Yeah, so maybe just give. So let's start with M star of A. That's what we wanted. Right. So now use the fact that E1 is measurable and therefore this is going to be same as M star of A intersection with E1 plus M star of A intersection with E1 complement. Right. Now use the fact that E2 is Lebesgue measurable. Therefore, this is same as A intersection with E1. The first one I will have as it is, and then the second one I'll have it as A intersection with E1 complement intersection with E2 plus M star of A intersection with E1 complement intersection with E2 complement. Right. So which I will write it as M star of A1, A intersection with E1 plus M star of A intersection with E1 complement intersection with E2 plus M star of I will write it as A intersection E1 union E2 Full complement. Yeah, so I wanted to use the subadditivity. That's what I wanted here. Yeah, so m star of A intersection with E1 plus m star of A intersection with E2 intersection with E1 complement, right? Yeah, so this I will have so that I can just use it here so that I'll have it as m star of A intersection with E1 union E2 plus m star of A intersection with, right, and that's exactly what we wanted, right? Yes, and we are done, right? So I'll stop here. If you have any questions, please. If you don't have questions, yes, Neil.
Sir, in the above, I mean,